start with the four fundamental. Let's continue with the fundamental subspaces and specifically see what the other two fundamental subspaces are besides the column and the null space. So the four fundamental subspaces. Four fundamental subspaces. So we cannot write them just by inspection. We cannot write them just by inspection. So the four fundamental subspaces cannot be written by inspection and a systematic procedure is necessary, which we are going to discuss today. A systematic procedure is necessary. When rank is n, when rank R is n, matrix has a left inverse. When rank is m, matrix has a right inverse. Matrix has a right inverse, and we'll see in a little while by the end of this lecture why is that so. Or when rank is m equals n, we have matrix as a two-sided inverse. This essentially means it's a square non-singular matrix. Okay. So we'll hopefully end the chapter by answering the uniqueness and existence properties of the inverse of a matrix. So column space of A, we know, has dimension R, which is R. R is the number of independent columns. This is the number of independent columns. This is the number of columns, number of pivot variables, number of pivots in U, and corresponding to the number of columns in A. The null space of A has dimension n minus R. This is also called, by the way, this is called the range. And null space of A is called the kernel. It's also called the kernel, and this is called the range. So the null space of A has dimension n minus R, and this is equal to the number of free variables. Okay. Row space of A, which is column space. Row space of A is equal to the column space of A transpose. So this can be written as column space of A transpose. The column space of A transpose is actually the row space. So row space of A is actually the column space of A transpose. This also has dimension R, because we have already said the number of independent rows is equal to the number of independent columns. This is equal to the number of independent rows, which is again equal to the number of pivots. And then finally, the fourth one, so 1, 2, 3, the fourth one. So the null space is actually also the right null space. So the left null space, of A is actually the right null space of A transpose. And left null space of A is the right null space of A transpose and contains vectors y such that A transpose y equals 0, 0 or y transpose A equals 0. So this is actually a n by m matrix. This is m by 1. So this is m by n. This is 1 by m. So we have a 1 by n row vector over here. So this is actually a row vector. This is a row vector. Maybe if you want, I can put a transpose on top of it, but we know this is a row vector. So left null space of A, which is denoted like this, has dimension R. So, has dimension m minus r. Has dimension m minus r. So in general, actually, in general, number of columns equals rank of the matrix equals the rank of the matrix. So maybe we do it later on. Equals the rank of the matrix equals the rank of matrix plus number of free variables. So if A is m by n, this is n equals r plus n minus r, and when A is n by m, which means it's A transpose, so we have m columns, rank is still r, and this has to be m minus r. So dimension of column space, dimension of null space, dimension of row space, no need to put this dot here, dimension of row space, this is the dimension of left null space, and this is the dimension of null space, or the right null space. So your right is actually it's not necessary. So when we say the null space, it's always meant it's right because x is on the right of A, or post multiplies A. So this is when we have A transpose, this is when we have A. So these are actually, this is how the dimensions of the various subspaces is tied. And we can also say C. So dimension of column space is so column space, and so column space has m components. So the vectors in the column, the vectors that generate the column space have m components, and similarly the vectors in the left null space, also have m components, Therefore, column space and the left null space are subspaces of Rm because number of components in the vectors that generate these spaces is m. Similarly, the row space, because it's the number of rows in m by n is n, component is n, and the null space are subspaces of Rm. So there are two in Rm, and there are two in Rm. Why? Because the number of components number of components in the vectors that generate these spaces is n. Okay, good. So let's look at an example for different matrices and see whether we can find the column space and null space of all these. Okay. So let's look at an example. So example 1, A equals 1 0 0 0 0 0. It's already in echelon form. This is a pivot. So this is 2 by 3. So rank R equals 1, because this is the only independent column, is equal to 1 independent column, or is equal to 1 independent or non-zero row. Good. So the dimension of the column space is 1, dimension of the row space is 1. So column space contains multiples of 1 and 0. So it's a subspace of R2, because 1 and 2. So this column space. Row space contains 1 0 0. This row, this was a column, this is the row, is a subspace of R1 2 3 R3. So this is M, this is N. What about the null space? So since rank R is 1, so let's look at the null space. So for the null space, dimension is n minus r, which is equal to 3 minus 1 equals 2. So we need 2 independent vectors generate null space of A. And what are these 2 independent vectors? So the free variables are second and third. So null space contains, again, this is a subspace of 3, because there are 3 unknowns. So one come here, other here. So the free variables are at positions 2 and 3. So only the first column is independent. The others are 2 and 3. So this is 1 0 0 1. So these are the free variables. And this one is 0. This is also 0, because this is this 0 goes here, and this 0 goes here. So it's 0 1 0 0 0 1. These are the vectors that generate and there are 2 of these. There are 1 and 2. So these are the 2 vectors. So these are 2 vectors that generate the null space. What about the column space, the row space? So the left null space. So the left null space is actually simply is generated by y transpose A equals 0. So this is simply 0 and 1. So this is simply 0 and 1 implies left null space of A transpose contains 0 1, because when you pre-multiply by, so when you pre-multiply y over here, you want to actually pick this row, which simply means you pick you make this element 1 and the other element 0. Or there is another way, or the other way is you find A transpose. So A transpose is 1 0 0 0 0 0. Okay, so this is the pivot. So again, rank is 1, and there are 2 variables here. So there are two ways. So there is one free variable here. So this is the free variable. So this represents free variable. If this represents the free variable, we say this implies null space of A transpose contains. So it's only two. So this is the free variable. It's the free variable. And this is this 0 over here, which goes here, right? And which is exactly the same as this before. So it's either way, either you look at the combination of rows or you look at A transpose and find the right null space over there. Okay. Second example, A is 1, 2, minus 1, 3, 6, minus 3, 3, 9, 3, 2, 7, 4, and we have looked at this matrix a lot, and I can do minus 2 R1 plus R2 minus or plus R1 plus R3 plus R1 plus R3. If I do that, I get 1, 3, 3, 2. Minus 2 plus 2 is 0, minus 6 plus 6 is 0, minus 6 plus 9 is 3, minus 4 plus 7 is 3, 1 minus 1 is 0, 3 minus 3 is 0, 3 plus 3 is 6, this is 6, and then what I do is I say minus 2R2 plus R3. When I do that, I get 1, 3, 3, 2, 0, 0, 3, 3, 0, 0, minus 6 plus 6 is 0, minus 6 plus 6 is 0. This is U, or what I can do is I say R2 divided by 3. If I do that, this is 1 and 1. So this is my U. This is my U. And what I can do is I can get rid of this 3 and I say minus 3R2 plus R1. If I do that, I have 0, 0, 1, 1, 0, 0, 0, 0, 1, 3, minus 3 plus 3 is 0, minus 3 plus 2 is minus 1, and this is my R, right? So either I can stop here or I can stop here. For the null space, I have to stop at R. Otherwise, if I just want to see the rank, I can see it from here. So number of, so from here, number of pivots equals number of independent columns equals number of independent or non-zero rows. This is equal to, this implies R is equal to rank. So R is equal to 1 and 2. So rank is 2. This implies dimension of column space of A equals the dimension of row space of A, and this is 2. This is 2. And what are the two independent columns? So column space is generated by this column and this column. So I can write, so column space of A contains 1, 2, minus 1 and 3, 9, 3. So the column space of A is generated by these two vectors. So these are the two, 1 and 2. What about the row space? So row space, since elementary row operations do not change the linear combination, or elementary row operations are actually linear combinations. So either I can pick this row, I can pick this row, or I can pick this row and this row. Both will give me the same answer. So let me pick the rows of R. So column space of A transpose contains non-zero rows of U or R, and these are 1, 3, 0, minus 1, 1, 3, 0, minus 1, and 0, 0, 1, 1. Why? Because elementary row operations elementary row operations are in fact linear combinations, linear combination of rows. This is not true for the columns, but it's true for the row space. Are in fact linear combinations of rows. Okay, good. What about the null space? Null space we have already calculated. So this, as I mentioned, this has two vectors. This has two vectors. What about the null space of A? Do I need to specify anything? No, sorry. So null space of A can be calculated from ux is equal to 0 or rx is equal to 0. So null space of A is equal to the null space of u is equal to the null space of R. Because again, we are doing linear elementary or row operation, which are just linear combinations. So let me write R here, 130 minus 1. So R is 130 minus 1, 0, 0, 1, 1, 0, 0, 0, 0. So this implies null space of A. So pivot. So first variable and then third. So third and first are pivot variables. Second and fourth are free variables. Are pivot variables, and second and fourth. This implies second and fourth are free variables. So null space of A contains four elements, combination here. So the second, fourth. So these are the free variables, either 1 or 0 alternately. This 3, 0 here, this minus 1 here. So this becomes minus 3, this becomes 0, this becomes plus 1, this becomes minus 1. So these are free variables. Alternately taking on values 1 and 0. So this is the null space again. A dimension of null space of A is n minus the number of free variables is number of free variables, which is equal to n minus r, which is equal to 4 minus 2, which is equal to 2. And again, I have one variable here, two variables here. Okay. What about the null space, left null space? What about the left null space? So the left null space So in left null space, we again look at Y transpose A. Or let me find it for you. So left null space of A is the dimension of the left null space of A is m minus r. M is 3, so this is 3 minus 2, so this is 1. So we have only one vector, implies only one vector that generates the space, this space. And obviously this is a line because all multiples also can generate this left null space. So what we do is we look at A transpose, or so all we need to do is find a vector here, Y transpose, find a vector here, which multiplies here. I get this 0 row of zeros. And actually the easiest one is if I find the inverse of L, but forget about it and let me do A transpose. So A transpose is, let me see, A transpose is 1 3 3 2, 2697, and minus 1, minus 3, 3 and 4. So transpose only exchanges the rows and the columns. And now if I do three operations, minus 3 row 1 plus row 2, minus 3 row 1 plus row 3, and I do minus 2 row 1 plus row 4. If I do that, I get 1, 2, minus 1, and then I get 3, 6 minus 3 becomes 0, minus 6, this is 0, plus 3 minus 3, 0, so everything else will probably become 0, so no, probably. Minus 3 plus 3, 0, minus 6 plus 9, 3, plus 3 plus 6, 6, minus 2 plus 2, 0, minus 4 plus 7, 3, minus 4 plus 7, 3, plus 2 plus 4, 6. And then if I do minus row 3 plus row 4, I will get 1, 2, minus 1, 0, 0, 0, minus 3 plus 3, 0, minus 6 plus 6, 0, so 0, 0, 0, and then I do row 3 divided by 3, so I get 0, 1, 0. So this is a pivot. This is a pivot. I can also do one more. I can do minus 2 row 3 plus row 1. If I do that, so 0, 0, 0, 0, 1, 0, 0, 0, 0, and so this is a pivot. This is one pivot. Minus 2 plus 2, minus 2 plus 2 is 0, and this is minus 1. So now I have this column is independent. So with this one I have three unknowns. So 1, and then this will be second column is independent. Second column with the pivot is independent. So this is third. This is the free variable. This is represents free variable. So column represents free variable, and this null space of A transpose contains 3, and this is actually 1, 0, 0. This is all right. That side, and 1 goes on that side, and this is 0 and 0. Yeah, this so 1, 0, 1. I'm sorry, 1, 0, 1, 1, 0, 1. This is all right. So if I do 1, 0, 1, I think maybe I've made a mistake over here. 1, 2, minus 1, minus 3 plus 3 is 0, minus 6 plus 6 0, plus 3 minus 3 is 0, minus 3 plus 3 is 0, minus 6 plus 9, 3, plus 3 plus 3, 6, minus 2 plus 2, 0, minus 4 plus 7, 3, plus 2 plus 4, 6, and then I do minus 3 minus 4, this goes away. I'm sorry, this is not 0, this is 2. This is 2, because if I divide by 2, so if this is 2, this is, I'm sorry, this is 2, and then I do minus 2 RC, so this is minus 2 plus 2, minus 4, minus 4, minus 1, this is becomes minus 4, minus 1, this is minus 5. This is minus 5, so this becomes 5, this becomes minus 2, and this becomes 1, because this equation gives x1 minus 5x3 equals 0, and this equation gives x2 plus 2x3 equals 0, and obviously x3 equals x3 equals x3. So this is the free variable. This is the free variable x3. If this is free variable, so this is minus 2x3, this is plus 5x3, and we can check if we have 5, minus 2 and 1. So let's check the original one. If I have 5, minus 2 and 1, so if over here I have 5, minus 2 and 1. So first row is multiplied by 5, second row is multiplied by minus 2, and last row is as is. So 5 minus 4 is 1, 1 minus 1 is 0. 5 into 3 is 15, 15 minus 12 is 3, 3 minus 3 is 0. 5 into 3 is 15, minus 18 is minus 3, minus 3 plus 3 is 0. 5 into 2 is 10, 10 minus 14 is minus 4, minus 4 plus 4 is 0. So whenever you pre-multiply, so whenever you pre-multiply, let me get rid of this one. So this is multiplied by 5. Whenever you pre-multiply a matrix, pre-multiply a matrix by a row vector, you are actually changing by a row vector. You are actually taking combinations of rows of the matrix. And whenever you post multiply, you are actually taking the combination of the columns of the matrix. So this one is all right. So this one is all right. So this is one vector, and this gives you the same result. And another way of finding this matrix is, which you can go home and do, rows of A combine to produce m minus r 0 rows of U. Here m was 3, r was 2. So 1 0 row of U, which was this one, 1 0 row of U, this one, or this one, whatever you want to take it. So 1 0 row of U, and since PA is equal to LU. So all you need to do is find L for this example. PA is equal to LU. This implies L inverse PA equals L inverse LU. So this is I. So this is equal to U, or this one is last m minus r rows of L inverse P. You don't need a P. P in this case is an identity because you're not commuting the rows. Are a basis of Y in left null space of A. Because why? Because they multiply A, or take combination of rows of A to give multiply A to give 0 rows in U. They multiply A or combine rows of A, to give 0 rows in U. Okay, so let's do one more example and then we move on to the inverses. Example A is 1, 2, 3, 6. This I can write as, we have done this before in chapter 1, L U. So this is L, this is U. So this is 1, 0. It's a upper triangular matrix. So it's lower triangle, this is lower triangle, this is upper triangular. 1, 2, this is 0, and this one is minus 3. So we are doing minus 3 R1 plus R2. So obviously this is going to be 3, inverse of this one, negative of this one. So this is 3, this is 1, and this one is minus 3 R1, and this should be 0. Okay, right? So if you multiply, when you're multiplying by this one, you're picking the first row. When you're multiplying this by, you are actually taking the, again, the multiple of the first row. There is only one pivot. Number of pivots equals 1. This implies rank is equal to 1. So dimension of column space of A equals 1. Dimension of row space of A equals 1. So which is the independent column? So this is the independent column. So we have column space of A contains, or is generated by, contains 1 and 3, or is generated by 1 and 3. The row space of A contains, or is generated by, this one, 1 and 2. The null space of A contains, so all the spaces are actually lines. Null space of A contains, so this is already this is already in the reduced row echelon form. So this one contains 1, this goes here, it's minus 2 and 1, right? Minus 2 and 1, and left null space of A contains, so now you have a vector over here. This vector is minus 3 and 1, probably minus 3 and 1, or is generated by this one. Okay, so let me draw this picture. If I put it here, so let me draw this picture over here. Actually, m is equal to n is equal to 2 in both the cases. So this is 1 and 3. So 1 and 2. So 1 and 2 is like this. So this point is 1, this point is 2. So there's a point over here. So this is some, so this is the row space of the matrix. So this is Rn, which is R2, and this is Rm, which is also R2. Okay. So the next other would be the null space. So null space is this one, which is minus 2 and 1. So minus 2 and 1. So this goes like this. So minus 2 and 1. This is actually a triangle. So this is all right. I've got it. So we'll see in chapter 3. These are at right angles. So this is the null space of A. So this is some xn over here. This is xn. This is some vector x. This is some vector xr. This is origin here. This is the origin here. This is minus 2 and 1. So x is minus 2, 1. Again, this is like this. So this is actually okay. So this is minus 2 and 1 somewhere over here. This is the column, this is minus 3 and 1. So x is minus 3 and 1. So this is the null space of A transpose. And then, so this is the null space of A transpose. And only one left is the column space here, which is 1 and 3. So 1 and 3, so it's a positive thing here. This is the column space of A. So all multiples on this thing go there. So what happens is, this over here we have some B. So this maps to this one. This is AX equals B. This maps to this point, AXN equals 0, and AXR obviously also maps to this point. This is AXR, this is AX equals B. Okay. So the null vector maps to the origin by this matrix, and all others. So these are also at right angles, and we'll see in chapter 3 that they are at the subspaces. The column space and the left null space are right angles, and they are called the orthogonal complement of each other. So the last topic in today's lecture is on existence of inverses. Existence of inverses. So if AC equals I, this means C is the right inverse, If AC equals I, this means this is the right inverse. And when it's the right inverse, and with the right inverse, an inverse exists, only when rank is as large as possible, So keeping this in mind, when the rank is as large and possible, so A is m by n, this is obviously n by m, so this is I m. And if B A is I, so this is m by n, this is obviously n by m, so this is I n. This B is called the left inverse because it's on the left of the matrix A. So here, so an inverse exists only when the rank is as large as possible. Let me move this one to here. Okay. So an inverse exists only when rank is as large as possible. What is the maximum rank here? So if R is equal to n, so here R is, this implies R is less than equal to n. R is less than equal to n. And here R is less than equal to, here R is less than equal to m. And here rank is less than equal to n. So if R is equal to n, this implies what? So if R is equal to n, so R is less than equal to n means this is a tall matrix. This is a fat matrix or a tall matrix. So this is a tall matrix. This is a tall matrix. And here this is a fat matrix. Implies a fat matrix. So when R is less than equal to m, we have what? So when R is less than equal to m, or so inverse exists. So C exists when R is equal to m. And this implies what? So when R is equal to m, this means the column space is all of Rm. This implies column space of A is the entire space. Rm this implies Ax equals B always has a solution. Okay. And if R is equal to n, this means what? this means, so if R is equal to n, if R, so either rank is less than equal to n, here rank is less than equal to m. So if R is equal to m, so B exists. So same thing. So let me write this here. B exists when R is equal to n. When R is equal to n, when R is equal to n, this implies if R is equal to n, there are no free variables. There are no free variables implies no free variables, or this implies, so there's only one solution, so this implies one unique solution, right? So one unique solution exists, if any. Okay, good. If this is the case, and only for the square matrix, and for a square matrix where R is equal to n is equal to m, left inverse equals the right inverse. Only for the square matrix A inverse is equal to A inverse A, otherwise it's not true. So let's see existence. So this is existence. And this is uniqueness. And this one is uniqueness. Let's see. So for the existence case, R is equal to m, Ax equals to B has at least one solution X, for every B. Why? Because columns span Rn. So A has a right inverse. A has a right inverse C such that AC equals IM. AC equals IM, and this is possible only, and is possible only when m is less than equal to n. Okay. And what about uniqueness? So uniqueness में R equals n, Ax equals B has at most one solution, X for every B, because columns are independent, or there are no free variables, or there are no free variables. And this means A has a left inverse B such that B times A equals IN, and is possible only for n less than equal to n. And what are one-sided inverses? So one-sided inverses, we have actually, so if Ax equals B, So if AX equals B, then A transpose AX equals A transpose B. A transpose A is n by M into M by N. So we have N by N, or this implies X equals A transpose A whole inverse A transpose B, or or B equals A transpose A whole inverse A transpose. This is the left inverse. So this one is the left inverse, left inverse. Similarly, uh, similarly, 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 AC should be equal to I. If AC is equal to I, then this implies C is equal to A transpose into A transpose inverse. Yeah. This is M by M, and this is N by M. So this is N by M. C is N by M. And this is M by N, and this is non-singular if R is equal to M. And this one is N by N, and this thing is non-singular if R equals N. Okay. Let me do an example. Here. For example, A equals 40050. So this is 2 by 3. So this is M, this is N. So R is equal to M equals, so this is a pivot, So R is equal to M is equal to 2. So this implies C exists. So C is the right inverse. So right inverse exists. So AC, so this implies AC equals 40050. C is going to be N by M. N by M is 3 by 2. So this would be 1 by 4, 0, 0, 1 by 5, some alpha and some beta, right? And this will give you I2, and many right inverses exist. One specific right inverse is C equals to this one, A transpose A transpose inverse. So A transpose A transpose inverse. So which is equal to A transpose is 400050, and A transpose is into A transpose inverse, where A times A transpose is simply 400050 into 400050, which is equal to 160025. And A transpose inverse is simply 2516 divided by this. So this is 1 over 16, this is 1 over 25. This is 0, 0, or C is equal to 400050 into 1 over 16, 0, 0, 1 over 25. Which is equal to 1 over 4, 0, 0, 1 over 5, and 0, 0. Caution, note of caution, a rectangular matrix cannot have both existence and uniqueness. Okay, so a square matrix has only one inverse if it exists. A square matrix, and all these statements are identical. A square matrix has only one inverse, if it exists, and this implies A is invertible if, so these are 8 statements. 1, columns span Rn, because it's a square matrix. Columns span Rn, columns are independent, it's one and the same thing. Rows span Rn, because it's a square matrix. Rows are independent. Elimination can be completed. So we have a full set of pivots. So elimination can be completed with n pivots. And finally, the determinant of A is non-zero. So we have done all these. The only two that you have not done are 0 is not an eigenvalue, and we'll see the product of eigenvalues is the determinant. So obviously, if the determinant is non-zero, you cannot have 0 as an eigenvalue. And finally, A transpose A is positive definite. Positive definite simply means, is in simpler terms, that the determinant of this one is greater than 0, is positive definite. Before we end today's lecture, what are matrices of rank 1? Matrices of rank 1 are also very important. So A is equal to 2, 1, 1, 4, 2, 2, 8, 4, 4, minus 2, minus 1, minus 1. This can be written as, this is rank 1, so rank here is 1. So you can go home and check that the rank is 1. If the rank is 1, I can write this one as 1, 2, 4, minus 1. And here I can write 2, 1, 1. So this is simply U into V transpose. U is this vector, V is this vector. So all rows are multiples of V transpose, and all columns are multiples of U. So since the rank is 1, this implies column space, row space are lines in Rn, and all columns all rank 1 matrices, all rank 1 matrices can be written in terms of column times a row vector. Column vector times a row vector. A row vector times a column vector is the inner product. That's a scalar. But a column vector times a row vector is the matrix. It's a matrix. So this is n by 1. This is 1 by m. So this is m by 1. Sorry. This is m by 1. This is 1 by n. So this gives us m by n matrix. So the last topic that we'll cover in the next lecture is on linear transformations. So again, if you have any questions, you can either email me or we can discuss in the Mondays or the Wednesdays. Thank you.